So in previous video I talked about this single slit diffraction and we found the condition for minima. So in this video I'm going to talk about the intensity distribution in a single slit diffraction. So first you see this pattern on the screen. So this is a single slit diffraction pattern and you see that the intensity is not uniform. At the center the intensity is high or larger, then it reduces slowly, and then there is a minimum, and then there is a maximum, but the secondary maximum has less intensity as compared to the principal maximum. So we are going to find a condition for this intensity distribution. So this is the single slit diffraction pattern. Here we have a source of light and this is very far from this slit, and this slit is a rectangular slit whose length is a. So there is a lens, converging lens. This is how we achieve this diffraction condition in the laboratory, and this is our screen. So now I can divide this slit into two equal parts. So each part will have a length a by 2 and a by 2. So this is one part and this is another part. So now assume that there is a ray that is originating from this central point, and let's say there is a length element, a very small length element dl. So this is a very small length element dl, and the light is originating from this dl portion, and it passes through this lens and is focused at this point P, and this P is an arbitrary point. So we want to find the condition for intensity at this point. So the ray that is originating from this dl length element and is focused as P, so for that length element I can write, because this will have an electric field component, so this can be written as dE naught electric field component due to this length element dl divided by r is the distance that it travels to reach at point P, into sine of omega t minus kr. Omega is the wave number, you know, and k is the omega is the angular frequency and k is the wave number, which is given by 2 pi by lambda, and r is the distance, and this a is the proportionality constant, or you can say this is entire thing is the amplitude of this field component. So this is for this wave, and now there will be another wave that is originating from this upper portion, and let's say this portion also have a length of dl, and there will be a wave that will be originating from this lower portion of length element dl. So look here, the ray that is originating from this upper point or upper length element has to travel less distance as compared to this ray, because this point is close to the upper end. So you know how we can find this path difference. We have already done this multiple times. So you draw a perpendicular from this point on this line r in such a way that after this point these two distances are equal. So this is the extra path which is represented here by delta. So this is the path difference. So we can write the equation for this point P due to for ray A1 dE1, the electric field due to this ray A1 that is originating from upper length element is A dl by r into sine of omega t minus k. I am using the same equation, but now it travels less distance, so this can be written as r minus delta, because this is equal to r minus delta. And similarly for this lower length element, because it travels more distance as compared to this distance, so this length will be r plus delta, because this distance is delta. So for this lower length element I can write dE2 is equal to a dl by r into sine of omega t minus k r plus delta. So this is equation 2. So these two equations are giving us the electric field due to these two portions. So if I want to find the combined electric field due to these two portions, so I can add them. So if D is the net electric field component due to these two, so I can write this equation. So I can add, so if I add these two equations, so this quantity can be taken common, and next we have this is as it is and this is as it is. So now there is a trigonometric identity. If we have sine of A plus sine of B, So this is equal to 2 sine of a minus b divided by 2 into cos of a, sorry, this is plus and this is minus a minus 2. So we can use this identity here. So this is as it is, and now 2 from our identity and then sine of this plus this. So omega t plus omega t, 2 omega t minus kr gives us minus 2 kr, and k delta minus k delta gives us 0. So divided by 2 according to our identity. Next we have this cos, and cos of omega t minus omega t 0, minus kr plus kr 0, and k delta plus k delta 2 k delta by 2. So I can take this 2 outside, and now we have sine of omega t minus kr because we can divide this. So this also gives me cos k delta. So since we know this delta is what, delta is obviously a by 2 sine theta, but in general we can say this is L sine theta. I am naming this as L, although we know that this is a by 2, but this is, I can name this as L sine theta instead of a by 2 sine theta because we have this length element dl, so we need to integrate this. So now this is the electric field component due to these two portions. So if this is slit, so I have taken these two portions and this gives me this result. So if I want to find the electric field component due to all these portions, so I need to integrate. But look here, this entire length is a, but we don't need to integrate it over a, because if I take this portion, so this result is for upper portion and lower portion. So all we have to do is to integrate for. So if I integrate this over this portion, only this portion, so this portion will be taken into account. So if E is the net electric field due to all the waves that are originating from this slit, so I can integrate over 0 to a by 2, and all we have to do is now to integrate this. So I can rearrange this expression, so this E as it is, and now 2a by r sine of omega t minus kr, because this is constant, and 0 to a by 2 cos of kl sine theta into dl. So integrating this, it gives me sine kl sine theta by k sine theta 0 to a by 2. So this gives me 2a sine of omega t minus kr by r as it is, and k sine theta, this k sine theta, and sine of ka by 2 sine of theta. So look here at this angle, so I want to make these same at this denominator. So if I multiply this by a, so I need to multiply this by a, that is dividing and that is using this. And next we need to get 2, so this 2 is here, so I can bring it here, so this gives me a by. So rearranging this, so I will get a by r into sine of a by 2 k sine theta, a by 2 k sine theta into sine of omega t minus kr. So next I can name this angle as alpha. So this gives me a by r into sine of alpha by alpha into sine of omega t minus kr, where alpha is equal to a by 2 k sine theta. So if I call this entire factor as its amplitude, so this gives me E is equal to E theta into sine of omega t minus kr, where a theta is equal to this factor and alpha is equal to this. So this is our equation of electric field at our point P due to all the waves that are originating through the slit. So you know that the intensity is proportional to the mod square. So I can take this intensity, and E theta is given by this expression. So taking its square, it gives me a square by r square into sine alpha by alpha whole squared, and there should be a proportionality constant, let's say it is a k. So this factor become maximum intensity. So now this expression gives the intensity variation in terms of theta, because alpha depends on. Okay, now let us find the condition for maximum. In previous video we found the condition for minimum, so in this we are going to find the condition for. Look at this expression. So this, if this alpha goes to 0, so if alpha is 0, then theta is 0, of course, because alpha is proportional to sine theta. So if I use this limit, in limit alpha approaches to 0, so this expression gives me I theta is equal to Im limit alpha approaches to 0 sine of alpha by alpha, and this is a well known theorem in this calculus, so this gives me 1. So this gives me maximum intensity. So we will have maximum intensity if this alpha approaches to 0. So this gives me principal maximum. Next, if we have sine square is equal to 1, look here at this expression. So if sine square is equal to 1, then we have I maximum by alpha. So if sine square alpha is equal to 1, then we have sine alpha is equal to plus minus 1, and alpha will be plus minus pi by 2 plus minus 3 pi by 2. So I can write in this way. So alpha is equal to 2m plus 1 pi by 2. So this, or in other words, I can put the value of alpha. So this is alpha is equal to a by 2 k sine theta. So also this k is equal to 2 pi by lambda. So putting it here, so I get this condition. So this is the condition for secondary maxima. So for m is equal to 0, we get the first secondary maximum, and from 1 to we get next order maximum. And from this expression we can also find the condition for minima, although we have already found this condition. But now look here, if I theta is equal to 0, so it means this sine square alpha should be equal to 0, because this is minimum intensity. So this function is 0 only if sine square alpha is equal to 0, and from here I get this value 0 plus minus pi plus minus 2 pi and so on. So alpha is equal to m pi. But also we know that alpha is equal to half k sine theta, and this k is basically 2 pi by lambda. So solving this expression, so this gives me a sine theta is equal to m lambda. We have already found this in the previous video. So now I can also plot this intensity versus this alpha, because alpha, you know that alpha is also a function of theta. So we are plotting this intensity against alpha. So you know that at the center, when this alpha is equal to 0, we have a maximum point, and the first minima occur at, from this expression you can look here, the first minima will occur at alpha is equal to plus minus pi. So these are the minimum point, and the next will be minus 2 pi and plus 2 pi. So these are the minimum points, and this is our maximum point. Also this is how we can plot this intensity. So this is the maximum intensity, and it is sine square alpha by alpha square, so it decreases by this function. So this is basically this decrease, and then we have the minimum point and maximum point. So these are known as secondary maxima, and these are known as first minima on the both sides. So that was all for this video. So next video I will be talking about the resolving power and Rayleigh criterion. Thanks for watching.